and welcome back to Sudoku Swami's pencil and paper method. Today, before we solve a puzzle from start to finish at the end of this video, we're going to talk about another one of the most commonly occurring and one of the most helpful patterns in Sudoku: naked pairs. Now, if you don't know what a naked pair is, then I suggest you go back and watch lessons number 5 and number 6 in this pencil and paper series before continuing here, okay? Great. First, we'll do a quick refresher tutorial on what I covered in lesson number 6, including the different ways naked pairs are formed and the different ways we can find and use them. And then finally, we will look at what happens when several naked pairs with the same two candidates are connected to form a network, which are typically called remote pairs. So let's get right to it. There are basically 5 ways for us to recognize and enter naked pairs when we are solving a puzzle with pencil and paper. When there are 2 empty cells remaining in a house, or when there are 2 cells that are unaccounted for in a house, or when you have a 2 or a 3 line restriction, when you have coinciding conjugate pairs, and lastly, as a result of something I call a reduced triple. So let's take a look at these one at a time. Now, you should all know by now that when the puzzle is solved, every row, column, and 3x3 block, i.e. every house, must contain all the digits 1 through 9 with no repeats and no number left out. So when you have a house like row 3 here in this diagram, where 7 of the numbers are already filled in and there are only 2 remaining unsolved cells, those 2 cells must contain the last 2 digits that are missing. So because we already have 1, 2, 3, 5, 6, 7, and 9, we know with absolute certainty that these 2 empty cells must contain 4 and 8, because they are the only 2 digits left to complete that row. One of those cells must be a 4 and the other must be an 8, even though we don't yet know which is which. So we fill them in just like that. And likewise, down here in block 8, we have 1, 2, 4, 5, 6, 7, 8, which means these 2 empty cells must contain 3 and 9 one way or the other. One of those cells must be a 3 and the other must be a 9, even though we don't yet know which is which. And so we enter them just like that. Those are naked pairs. The 2 cells in row 3, each containing 4 and 8, are a naked pair, and the 2 cells in block 8, each containing 3 and 9, are also another naked pair. Each cell of those 2 naked pairs is called a bi-value cell. This is an extremely important term and concept for you to understand. First, because it is a very common but powerful little thing, and second, because you will hear me talk about bi-value cells over and over again in this series of lessons. A bi-value cell is simply a cell that has only and exactly 2 possible remaining candidates left in it. Bi meaning 2, just like a bicycle has 2 wheels. Therefore, it must eventually be solved for one of those 2 candidates, and knowing this helps us make various deductions. But because we will only be entering a few candidates by hand here and there in strategic places, and will not be seeing all the possible candidates for each and every cell in the puzzle, we will often see a cell with only 2 candidates in it, but this does not necessarily mean that it is a true bi-value cell. So we have to be extremely vigilant and be constantly aware of which of those cells with 2 candidates showing are indeed bi-value cells and which are not. This distinction is of critical importance, okay? And don't worry, I'll keep reminding you about it until you're sick of hearing it. Ha ha ha. Like for instance, this cell here in row 8, column 8 may only have a 2 and a 7 in it that we have entered for some reason or other. But this cell can only see the digits 1, 4, 5, and 6, which means it could actually contain the candidates 2, 3, 7, 8, and 9. So even though we are only seeing the 2 and the 7 right now, this is not a bi-value cell. Capiche? These cells that contain our naked pairs up here in row 3 and down here in block 8, they are bi-value cells, but this cell is not. I hope that's clear. A naked pair is always going to be composed of two identical bi-value cells that lie in the same house. And please note that I may from time to time refer to a bi-value cell as a BVC, okay? All right, let's move on to the next example. Notice that there are 5 empty cells in column 3, and there are also 5 empty cells in row 7. But let's take a closer look at what's really going on here. Up here in block 1, we have 6 of the 9 digits already placed. We have 1, 3, 5, 6, 7, and 8. So that means these 3 cells must be solved for 4, 2, and 9 one way or the other because they are the only 3 digits left to complete that block, that house. Does everybody get that? This is called a triple that I described briefly in lessons 5 and 6. Now, if you recall, we are normally not going to enter triples unless they are in a 2 by 2 by 2 configuration, meaning that each cell of the triple contains only 2 of the possible 3 candidates. And we'll talk more about that in the next lesson. But we can still make a mental note that these 3 cells must contain 4, 2, and 9 with respect to block 1 without actually filling them in. But notice that those 3 cells also lie in column 3. So because that triple is locked into block 1, that means those 3 candidates, 2, 4, and 9, cannot appear anywhere else in column 3, okay? So 2, 4, and 9 are already accounted for in column 3, and these other cells are already filled with 1, 8, 7, and 6. So that means these other 2 empty cells in column 3 are the only 2 remaining cells that are unaccounted for. So they must contain 5 and 3, because those are the only 2 possibilities left. That is a naked pair. Those are 2 identical bi-value cells that lie in the same house. Those 2 cells must eventually be solved for 5 and 3. So even though we have 3 empty cells up here in column 3, we know that they must contain 2, 4, and 9, which means that we can safely enter a naked pair of 5 and 3 into these 2 cells. And likewise, down here in block 9, we already have the digits 1, 2, 3, 5, 6, and 9. So that means these 3 cells must contain 4, 7, and 8. Okay? And since they are locked into block 9 but also lie in row 7, we know that 4, 7, and 8 cannot appear anywhere else in that row. And because 1, 3, 5, and 9 are already placed in row 7, we know that these other 2 empty cells must contain a naked pair of 2 and 6 because those are the only 2 possibilities left for row 7. So even though at first glance it looked like there were 5 empty cells in column 3 and in row 7, by recognizing the existence of the 2 triples without actually filling them in, we can see that there are really only 2 cells that are unaccounted for in each of those houses, allowing us to enter those naked pairs. Got it? Okay, let's go to the next example. Here in this diagram, let's first focus our attention on the top horizontal chute. And let's take a look at what's happening with row 2 and row 3 in relation to block 3. Notice that we have a 5 and an 8 already in row 2. So that means these 3 cells cannot contain a 5 or an 8. And we also have a 5 and an 8 in row 3. So that means these 3 cells cannot contain a 5 or an 8. And because of this 7 that's already placed in row 1, column 9, that leaves only 2 cells left for a 5 and an 8 to go in that block. So we can enter a naked pair of 5 and 8 into those 2 cells. This is a 2-line restriction, the 2 lines being rows 2 and 3. But notice that this only works because of the presence of this 7 up here in row 1, column 9. If that cell were empty like this, we would know that a 5 and an 8 must go somewhere into these 3 cells along with some other candidate, but that's all. We wouldn't know exactly how those 3 candidates would be distributed in those 3 cells yet, so we would just have to leave them blank for the moment. But with that 7 in there, that ensures that we have a naked pair of 5 and 8 in these 2 cells. And as you can see, we have the same situation going on in the central vertical chute. We have a 4 and a 2 in column 5, and we also have a 4 and a 2 in column 6, and they all lie outside of block 5. So that means there cannot be a 4 or a 2 in any of these 6 red cells. And again, because of the presence of this 9 in row 5, column 4, that leaves only 2 cells left in block 5 for a 4 and a 2. So we can safely enter a naked pair of 4 and 2 into these 2 cells. And here in this diagram, we have a 3-line restriction. We have a 6 and an 8 in row 5, we have a 6 and an 8 in column 7, and we have a 6 and an 8 in column 9. And they all intersect with block 6 in such a way that there cannot be a 6 or an 8 in any one of these 7 cells. So once again, we know there must be a naked pair of 8 and 6 in those 2 cells. And we can enter it just like that. So that is a naked pair. One of those cells must be solved for 6, and the other must be solved for 8. 2 identical bi-value cells that lie in the same house. And this time, because we have a 3-line restriction, we don't need any additional digit to block one of the cells to make this happen like we did with the 2-line restriction. The 3 lines are enough all by themselves. And on a side note, the term line in Sudoku is generally used as a universal term that can mean either a row or a column. This sometimes saves you the trouble of having to repeat the same sentence, first referring to the rows and then again referring to the columns. It helps to speed things up a little bit once in a while. All right, before we go to the next example, I'd like to make an important point. When we are doing the puzzles with pencil and paper, 9 times out of 10 when we find a naked pair, it is going to lie in 2 houses at the same time, like you see here. This naked pair of 8 and 6 lies in column 8, and it also lies in block 6. So it is said to be locked into those 2 houses, meaning that there cannot be another 6 or another 8 in either of the houses in which it lies, because one of those cells must eventually be solved for 6, and the other must eventually be solved for 8. But a naked pair only really needs to be in one house. It can be in a row, or a column, or a block. But it cannot look like this. These 2 cells, even though they contain the same 2 candidates, are not in the same house, so they are not related and do not comprise a naked pair. In order for the 2 cells to work together, they must lie in at least one house. And we will usually be finding them in the intersection of a row and a block, like this, or in the intersection of a column and a block, like this, i.e. in 2 houses at the same time. All right, let's go to the next example. Let's say you're working on this puzzle and you discover that this cell down here in row 9, column 5 is a 1. So now this 1 with these 2 other 1s tells us that we can enter a conjugate pair of 1s into those 2 cells just like that. Those are the only 2 cells in block 2 where a 1 can exist now. And then let's say you discover that this cell over here in row 3, column 8 is a 9. So now with these 2 other 9s, we know that we can place a conjugate pair of 9s into those 2 cells. Those are the only 2 cells left where a 9 can go. And then let's say you discovered that this cell in row 3, column 1 is a 2. So this 2, coupled with these other 2s, tells us that there is a conjugate pair of 2s in these 2 cells. Those are the only 2 cells in block 2 that can contain a 2. But now look what has happened. We know that one of these cells must be solved for 1, and one of them must be solved for 2, right? They are both conjugate pairs. So that means this cell cannot be a 9, which further means you can eliminate that 9 and solve this cell for 9, leaving a naked pair of 1 and 2 in these 2 cells. The conjugate pair of 1s and the conjugate pair of 2s have coincided in the same 2 cells, thus telling us that they are indeed a naked pair. And that's all there is to this one. Those are coinciding conjugate pairs. Everybody got that? All right, next one. Now here in block 5, we have 6 of the 9 digits already placed. We have 1, 3, 4, 6, 8, and 9. So we know that there is a triple remaining in these last 3 empty cells, right? They have to be solved for 2, 5, and 7 in some order. Now normally we will not be entering triples unless they are in a 2 by 2 by 2 configuration, but for this example, let's fill them in. Okay? And now let's say we discovered that this cell over here is a 2. Well, that means these two 2's have to be false, so you can eliminate those 2's and enter that 2, and this becomes a naked pair of 7 and 5, which means you can eliminate this 7 and this 5, and this becomes a hidden single on 2. And likewise, if we discovered this cell over here was a 7, we could eliminate these two 7's and solve that cell for 7, leaving a naked pair of 2 and 5 in these two cells, and a hidden single of 7 in this cell. So when you have a triple that lies within a block and 2 of the cells are in the same line, like these 2 cells in row 5, if any one of those digits is solved in that line outside the block, it will reduce the triple to a naked pair and a hidden single on the other candidate. So I call this a reduced triple. Got it? All right, let's say we have a naked pair of 7 and 3 in block 5, and we have another naked pair of 7 and 3 in column 6. Now these 3 bi-value cells are connected in such a way that they are either going to be solved for 7, 3, and 7, or they are going to be solved for 3, 7, and 3. That's the only 2 ways those 3 cells can be solved because of the way they are situated in relation to each other. So now let's take it one step further. Let's say we have another naked pair of 7 and 3 over here, another naked pair of 7 and 3 in column 1, another naked pair of 7 and 3 in block 7, and another naked pair of 7 and 3 in row 9. Okay? So now, as soon as we solve any one of those cells, that is going to dictate what goes in the other cells. Like for instance, if we solve this cell for 3, this has to be a 7, this has to be a 7, that has to be a 7, this has to be a 3, that has to be a 7, and that has to be a 3. These 7 identical bi-value cells form a network that looks like this. Those blue lines are connecting each set of naked pairs. And we know the solutions to these cells are going to alternate either 7, 3, 7, 3, 7, 3, and this one 7, 3, or they're going to alternate 3, 7, 3, 7, 3, 7, and 3, 7. So to better understand this, we can label these cells A, B, A, B, A, B, and A, B. Because we know all the A cells will contain the same number, and all the B cells will contain the same number. But I think it will be easier to color them like this: blue, yellow, blue, yellow, blue, yellow, and then blue, yellow. So we know that all the blue cells will be 7 and all the yellow cells will be 3, or the other way around. All the blue cells will be 3 and all the yellow cells will be 7. These are called remote pairs. And the consequences of this are that any cell that can see both a blue one and a yellow one cannot contain a 7 or a 3. Like this cell right here cannot contain a 7 or a 3 because it can see a blue one and it can see this yellow one down here. So we know that between this blue one and this yellow one, the 7 and the 3 are covered. So this cannot be a 7 or a 3. And likewise, there cannot be a 7 or a 3 in this cell, and there cannot be a 7 or a 3 in this cell, because they can both see a blue one and a yellow one. Does that make sense? But if there are any bi-value cells containing a 7 and a 3 elsewhere in the puzzle that are not connected to this network, like let's say for instance in this cell or in this cell, those cells could contain a 7 and a 3, and it would be unaffected by the network because they do not see any of the blue or the yellow cells. So when we are doing the puzzles with pencil and paper, the most important part of this is that anytime you solve one of the cells in the network, it's going to solve all the other cells in the network. But we can sometimes use the fact that another cell that can see both a blue one and a yellow one, or both an A cell and a B cell, cannot contain a 7 or a 3. Okay, that's it for this tutorial, so let's go ahead and solve today's puzzle. Okay, we've got 26 givens, and notice that 12 of those givens are right here in this middle horizontal chute. That's almost half of them. And when you see something like this at the beginning of a puzzle, it's probably a good idea to look for some naked singles before you start cycling through the candidates. So let's take a look at this cell that's smack dab in the middle of the puzzle here in row 5, column 5. This cell can see a 1, a 2, a 3, and it can see a 4. It cannot see a 5, but it can see 6, 7, 8, and 9. So that means this cell must be a 5 because it can see an instance of all the other 8 digits. So that is a naked single, and you can enter it just like that. And over here in this cell, in row 4, column 9, this cell can see a 1 and a 2, but it cannot see a 3, but it can see 4, 5, 6, 7, 8, and 9. So we know it has to be a 3. That is another naked single, and you can enter it just like that, and that's a great way to get this puzzle started. So now let's just cycle through all the numbers starting on the 1s and see what happens. So we've got a 1 here and a 1 here, and that means we can put a conjugate pair of 1s into these two cells. But notice this is a 2-line restriction. We have a 6 and a 1 in row 5, and we have a 6 and a 1 in row 6. So that means there are only 2 cells left in block 4 for a 1 and a 6. So that is a naked pair, okay? And there's nothing else on the 1, so let's move to the 2s. And because of this 2 and this 2, we can put a conjugate pair of 2s into these 2 cells. Those are the only 2 places left in block 5 for a 2. And then because of these 3 2s, we can crosshatch a 2 into this cell. That is a hidden single, and you can enter it just like that. And then because of these 3 2s, we can enter a conjugate pair of 2s into those 2 cells. And likewise, because of these 2 2s, we can enter another conjugate pair of 2s into these 2 cells. And notice that these 4 candidate 2s form an X-wing. So we know that one diagonal pair of those 2s will be true and the other diagonal pair will be false. And so as soon as we solve or eliminate any one of those 4 2s, we will immediately know the true-false value of the other 3. And now these 2 2s in row 9 are a conjugate pair, and so one of them has to be true. So they rule row 9, and this 2 rules row 8, and this 2 rules column 5. So we can put another conjugate pair of 2s into those 2 cells, and notice that they form another X-wing. So we have 2 X-wings on the 2s. And now all the 2s are accounted for in all 9 blocks, and that's what you want to look for. You should always check all 9 blocks to see if there is anything you can do with the number you're working on before you go to the next number to make sure you haven't missed anything, okay? So now let's move on to the 3s. We've got a 3 here, and a 3 here, and a 3 here. So that means we have a hidden single on 3 here in this cell in block 7 because of cross-hatching. And we can enter that as the solution to that cell. Which further means we can enter a conjugate pair of 3s into these 2 cells. And because of this 3, and this 3, we can enter another conjugate pair of 3s into those 2 cells. And there's nothing else we can do with the 3s right now, so let's move to the 4s. And because of this 4 and this 4, we can crosshatch a 4 into that cell. That is a hidden single, and you can enter it just like that. And now because of that 4 and this 4, we can enter a conjugate pair of 4s into these 2 cells. Now notice here in row 5, we have a 1-line restriction. These cells are already filled with 8, 9, 6, 1, and 5, and the 7 and the 4 block the rest of row 5. So there are only 2 cells in block 5 for a 4 and a 7 to go, and you can enter them as a naked pair. And now because the 1 and the 6 are accounted for in row 4, this cell also has to be 4 and 7. And now we've got a little mini network between these cells containing 4 and 7. Those are 2 naked pairs. And as soon as we solve one of them, we will know the value of the other 2. But notice, now there are only 2 cells left in block 5, so they must contain 2 and 3. That is another naked pair. Okay? And now because one of those 3s has to be true, this 3 cannot be true. That's like a ray gun, and that means you can enter the 3 as the solution to that cell. All right, so let's get rid of all those colors. And now we only have 2 cells left in row 5, and we only have 2 cells left in block 4. So they must be 8 and 9, okay? but we have an 8 down here in row 9, column 1. So this cell cannot be an 8. It must be a 9, which means this cell has to be an 8, and this cell has to be an 8. Does everybody get that? Because we had a naked pair of 8 and 9 in those two cells, and we had a naked pair of 8 and 9 in these two cells. But this 8 prevents this cell from being an 8, so it has to be a 9, and these other two cells must be 8s. Okay? And now, before we go to the 5s, notice that we have only 2 empty cells in column 1, so they must be 7 and 6 because those are the only numbers that are missing. But because of this 7 over here, this one has to be the 6, and this one has to be the 7. So you can enter those two numbers into those two cells. So now for the 5s, we've got 4 5s that are intersecting with block 7, leaving only one cell left for a 5 to go, and you can fill it in just like that. And now because of this 5 in row 3, and this one in column 4, and this one in column 5, we can put a 5 into that cell. And now we have 8 of the 9 5s already placed, so there's only one place left for a 5 to go in the whole puzzle, and that is right there. So we can enter that, and now let's move to the 6s. Now once again, in row 2, we have a one-line restriction. We've got an 8 and a 6. So that means these two cells must be filled with 8 and 6. That will be a naked pair, but because there's an 8 down here, this one has to be the 6, and this one has to be the 8, okay? And now that we know the solutions to these two cells, we know that this cell cannot be a 6, so you can erase that 6, and because this has to be a 1, this cannot be a 1, so you can erase that 1, and now we can solve all 4 of those cells. And this leaves only one cell left in block 1. That's a full house. This has to be a 9. So now we look down column 2, we've got 2 cells left, so this has to be a naked pair of 4 and 9 and 4 and 9. And now these 2 cells are the only 2 remaining cells in block 7. They have to be 1 and 7. And because there's a 7 over here, this cell must be the 7, and this one must be the 1. All right, now back to the 6s. We've got a 6 here, and a 6 here, and a 6 here. So we can put a conjugate pair of 6s into those 2 cells. And because of these 2 6s in column 7 and column 9, we can put a conjugate pair of 6s into those 2 cells. And there's nothing on 6 in block 8, so let's move to the 7s. So because of this 7 and this 7, we can put a conjugate pair of 7s into these 2 cells, and I think that's it for the 7s. So now let's move to the 8s. And now because of this 8 and this 8, we can put a conjugate pair of 8s into these 2 cells, and likewise, because of this 8 and this 8, we can put a conjugate pair of 8s into these 2 cells. And notice that these 4 8s form another X-wing. Now because of these 2 8s in column 5 and 6 and this one in row 9, there's only one place left for an 8 in block 8, and that is right here. And so now because we know this is an 8, this cannot be a 2, which means this must be a 2. And this was an X-wing on the 2s, remember? So this cannot be a 2, that has to be a 3, and if that's a 3, you can erase that 3, and you can enter all 4 of those numbers. Okay? And now there are only 2 cells left in row 7, and one of them has a 4 and a 9, so this one must also be 4 and 9. So now we have 2 mini networks. We've got one here on the 4 and the 7, and we've got another one here on the 4 and the 9, okay? So let's get rid of all those colors. And now let's take a look up here in row 2. We've got 3 cells left, and they have to be 1, 7, and 3. But we have a 1 and a 3 here, so this has to be the 7, which means these 2 cells have to be 1 and 3. But there's a 1 here, so this one has to be the 3, so you can erase that 3, and you can enter a 1 into that cell. And of course, we can enter the 7 into that cell. And now because of these 2 3s, we can crosshatch a 3 into this cell. That must be a 3. We can enter that. And now we only have 2 cells left in row 1, and they have to be 1 and 9. But there's a 1 down here, so this has to be the 9, and this has to be the 1, and you can enter both of those numbers. And now here in row 6, we have 3 empty cells, so they must be solved for 4, 7, and 9. But we've got a 9 here, and a 9 here, so that means this cell must be the 9, and this cell must be 4 and 7. So that means we've added another bi-value cell to this little network, and all 4 of those cells are interconnected now, and as soon as we solve one of them, we'll know the value of the other 3. So let's enter that 9, and let's get rid of those colors. And now because of those 3 9s, we can enter a conjugate pair of 9s into those 2 cells. And because of these 2 9s, we can enter a conjugate pair of 9s into these 2 cells. Now let's take a look at column 7. We have 3 empty cells left, and they must be solved for 4, 7, and 8. But this cell can see an 8 and a 7, so it has to be a 4. Okay? So let's mark this cell. That is a 4, which means this cannot be a 4. You can erase that 4. And this was a naked pair, so this cannot be a 9. And if this is a 4, you can erase that 4, and this must be a 9. Okay? Now, if this cell is a 9, you can erase this 9. Now, this cell has to be a 9. And if this cell is a 9, this cell over here is not a 9, and this cell must be a 9. And we can enter all of those numbers. Okay? So let's get rid of those colors. And now in column 9, we have 2 cells left. They must be 1 and 2, but because there's a 1 over here, this has to be the 2, and this must be a 1. So you can erase that 2, and this was a conjugate pair, so this cell is a 2. So that means it cannot be a 6, and that was a conjugate pair, so that means this cell is a 6, and it's not an 8, so erase that 8. This cell is an 8, and so this cell cannot be an 8. You can erase that 8, and this cell must be an 8, and because this is a 2 and this is an 8, you can erase that 2, and we can enter all of those numbers. Okay? And now there's only 1 cell left in block 3, and that has to be a 7. So that means these 2 cells become a naked pair of 4 and 6. And now we only have 2 cells remaining in row 8, and they must be solved for 1 and 4, but because there's a 1 here, this one has to be the 4, and this has to be the 1, and this is going to solve the whole puzzle. If this is a 4, you can erase that 4, and that must be a 6. If that's a 6, you can erase that 6, and that must be a 4. If that's a 4, you can erase that 4, and that becomes a 7. If that's a 7, you can erase this 7, and you can erase this 7, which means this becomes a 4, and this was a conjugate pair on 7, so that has to be a 7. And if this is a 7, this is not a 7, that has to be a 4. And because these 2 cells are 4, this is not a 4, and that is a 7. And we can enter all of those numbers. Leaving only 1 cell left in the whole puzzle, which must be a 6. And there you have it. That is how you do it. So that took about 12 minutes, but that's only because I spent a lot of time marking the cells for you and explaining each move. But this puzzle can be easily solved in less than 5 minutes. I was going to solve it one more time without talking, but this video is too long already, so we'll do that another time with another puzzle. Okay, that's going to do it for today. If you enjoyed this video, please click the red subscribe button, the thumbs up icon, and be sure to click the little bell icon if you would like to be notified of new video uploads. And don't forget, if anyone has a puzzle from a newspaper, a magazine, a puzzle book, or whatever that you would like to see me solve in a future video, please send it to me at sudokuswami@gmail.com, okay? In the next lesson, before we solve our puzzle, there will be a short refresher tutorial on what I call 2 by 2 by 2 triples. So I hope to see you all again right back here for that. In the meantime, be well and be happy.